Hello. Okay. So let me make this full screen. So welcome to this course of chemical crystallography by Professor Anshuman Rai Chaudhary from ISR Mohali. So this course had started on 25th of July, and the end date is 14th October. So the exam date is 29th October, right? And today is 15th October. So I'm the course TA, and every week we have been meeting in this link and Saturday 3 to 4 p.m. for this live session. And if you still have any questions, you can ask or post your questions in this ask a question tab in the SWAYAM portal, and the professor or the TA when they see, so they will be able to reply. So welcome to this live session number 12. So today we will be discussing assignment 10. Okay, so it's a kind of mistake. So today we will be discussing assignment 10. So before going to the questions and answers, we will first discuss about some concepts or topics which we will be required to solve. So this will be based on week 10, and the concepts will be used to solve the assignment of week 10. Okay. So we are talking about this X-ray diffraction of a crystal leading to reciprocal lattice points and the intensities of reflections and everything. So this X-ray. So what is X-ray? So X-ray is basically a wave, right? So what do we mean by a wave? A wave is something which repeats exactly in time with having a time period, and within a time period it covers a certain distance in space, which is called as the wavelength. So the time period is capital T, and the period or the distance is written as lambda. So what do we have? We have distance is equal to speed into time, right? So when we speak of waves being in phase, so waves can be in. So if we now go from one single wave to two waves, so when we have two waves, then the two waves can be in phase or out of phase. So waves are said to be in phase if the difference between the waves of the components is an integer multiple of 2 pi, and the waves are in opposite phase if it is an odd multiple. Okay, so we will now move on to solving crystal structures. So if we have a crystal, and then this crystal is diffracting, and we collect the 3D set of diffraction data. So the question, so as I was talking about in the previous session where we ended, so the question is whether the diffraction data has all the information which is necessary to completely determine the underlying structure of the crystal. So can the diffraction pattern be used to locate all the points in the unit cell containing the positions and the identities of the atoms? So the answer is yes in most cases. However, the phase information, since it is lost and we are not able to solve the structure without the phase information, then we need to use some kind of methods to get around the phase problem. So the first question is, the first one is the Patterson vector, Patterson map, or Patterson synthesis, and the second one is the direct method. So first we will talk about the direct methods. So in direct methods, what happens is a few strong intensities are chosen and their phases are assigned at random. Then relationships between the phases are sought for, and the phases are constantly modified until a consistent set is obtained. So this allows the calculated initial calculated structure factors, what we call, to be obtained. Then from there on the structure is improved. So what happens is when we are collecting the data, then at high angle, So if high at high angle the crystal which for which we are collecting the data, if the crystal diffracts nicely and gives nice diffraction spots at higher angle, it means at better resolution it is giving good data, then it gives the information about the finely spaced structure, the finely spaced features in the unit cell. In that case, what happens is the missing phase information can be reconstructed directly from the structure factor relationships or the mathematical relationships between the structure factors. Since the phases come directly from the observed diffraction pattern, since the phases come directly from the observed diffraction pattern. So that is why these methods are referred to as direct methods. So what is a direct method calculation? So a direct method calculation proceeds as follows. Okay, so at first the phases are chosen for a few strong reflections a few strong reflections are chosen and their phases are assigned at random. Then the phases for other reflections are generated using the phase relationship among the strong reflections. And once enough number of phases have been calculated, then the electron density can be calculated and can be interpreted in terms of atomic positions. Now, what happens is if the number of atoms in the structure keep on increasing, like for example, moving to more complex structures like proteins, for example, then the phase relationships become weaker as the number of atoms in the structure increases. And further, this approach only works when the data can be collected to high resolution. So, most proteins cannot be solved by this method. Why? Because the structure factors cannot be measured up to that resolution. Okay. So then so what did we say? So here we said that there are two methods which are commonly used, right? So this is the direct method which we discussed. Then another is the Patterson method. So now we will move to Patterson method. So what is the Patterson method and uh, where is it applied? So the structure of small molecules can be solved even in the absence of phase information. So while phases determine the position of the peaks of electron density across a unit cell, thereby giving information about the position of the atoms. Why? Because atoms are nothing but the electron densities, right? So the presence of a strong diffraction spot alone gives a strong indication that features must be present with the corresponding spacing. Thus, the structure factor magnitudes alone contain information about the spacing of atoms in the structure. And then this Patterson function is so before this I want to say what is the Patterson method. So this Patterson method was found out in 1934 by this person after whom this method is named. So the Patterson function is obtained by calculating a map by using squared structure factor magnitudes and with all the phases being set equal to 0. Instead of the peaks at the atomic positions, the Patterson map, what does it show? It shows peaks at every position which correspond to some interatomic vector. Interatomic vector means vector in between the atoms in the structure. So the Patterson function has been an effective tool for solving small molecule structures. However, its usefulness falls off quickly as the number of atoms increases. So if we have a structure with n atoms, then the Patterson function will contain n square minus n interatomic vectors, many of them overlapped. This approach becomes unusable for structures containing more than 20 to 50 atoms unless there is a subset of atoms with high atomic number. So what happens is, so if there are n atoms, we have n square minus n peaks. However, if there are few heavy atoms in the structure, then they form pairs which give rise to strong peaks and their positions can be guessed. And once the heavy atoms are located, then we can move with the Fourier transform to obtain the set of calculated structure factors which are compared with the observed structure factors, and the model is improved using an iterative procedure. Whereby this factor called as the R factor is used, where it signifies the difference between the observed and the calculated structure factors, and the lesser it is, the better is my model. So now we come to the question answers. So the first question, so we are talking about assignment 10 of week 10, right? So the first question was that area detectors like CCD are used in X-ray diffractometer to measure only the intensity of the diffracted X-ray beam which hits the detector surface. So the first question was that area detectors like CCD are used in X-ray diffractometer to measure only the intensity of the diffracted X-ray beam which hits the detector surface. So this is true. Then I hope you know the meaning of CCD, right? Charge coupled device. So the second question was that phase information cannot be obtained from mathematical relationship structure factors. So we just read, right, that in some cases the phase information can be obtained. So this is false. The structure of small molecules can be solved even in the absence of phase information if the crystal diffracts at high angle, giving better resolution data. So it is true. Which of the following does not pertain to direct methods? So what did we learn about direct methods? That phases are chosen for a few strong reflections. Then phases for the other reflections are generated using phase relationships between the strong or among the strong reflections. And this approach only works when data can be collected to high resolution. And information about the unknown phase may be obtained by making a known change to the contents of the unit cell and measuring the effect on the diffraction pattern. So the sixth question is that the sigma 1 relationship. So what is the sigma 1 relationship? So the sigma 1 relationship is applied in most of the cases of centrosymmetric structures. So if we have a centrosymmetric crystal, then for the centrosymmetric case, for every atom, so if we consider the atom J, so for every atom J at fractional coordinates xj, yj, zj, there has to be an identical atom at minus x, minus y, minus z, right? Why? Because of inversion center or centrosymmetry. In this case, the phase problem, namely the determination of the phases of Bragg reflections, becomes rather simpler because it has only two choices, either 0 or pi, which is 180 degree. In the non-centrosymmetric case, there is no center of symmetry and the phases can assume any value between 0 to 2 pi. So the sigma 1 relationship, so this question, that sigma 1 relationship is applicable for what type of system? So obviously the sigma 1 relationship is applicable for centrosymmetric systems. Then this next question says that if there is a center of symmetry, then the phases can be only 0 or 2 pi. But what is 2 pi? 2 pi is 360 degrees, right? Which means it is back to 0. So it is essentially the same. So so that is why it is false, because the true sentence will be that if there is a center of symmetry, then phases can only be 0 or pi, which is 180 degrees. So then this question, so this is also again a very interesting question, that we have been given two diagrams A and B representing two types of diffraction conditions. Then what should be the scattered beam as captured in the detector for A and B? So for this, so this is my case A and this is my case B. So here we have this wave. So this is my wave 1, this is my wave 2, and what are we seeing? From here we are seeing that it is coming in phase. So when this is the maxima, here is also the maxima if I try to draw a straight line. So here when it is coming, then the two waves are in phase. Now it hits, you can say, in a scatterer 1 and 2. So when it hits the scatterer, then what is happening? So the for this wave number 1, if we see, so after hitting the scatterer, here is the maxima coming, but in that same position in space, what do we have? We are having the minima for number 2. Then these means these two waves are not in phase, right? This is kind of a destructive interference. However, here when up to here it was in phase, but here they seem to be in phase, at least more in phase than this one, right? So here it is in phase, hence this is giving rise to what is known as constructive interference. So the intensity of the two waves in case of B will add up. It will add up. Hence the spot obtained will be of higher intensity in case of B, and it will cancel, the intensities of the two waves will cancel each other in case of A. So now let us see the two diagrams. So here these two options can be ruled out in the beginning. Why? Because the situation is not the same for A and B. So in any case it cannot have the similar detector. The detector cannot have similar response for A and B. So these two options are first of all incorrect. Now what are we seeing? That it will add up in case of B and it will cancel in case of A. So here it is adding up in case of A, so this is also not the right option. Here what we see, it is adding up in case of B and it is very light or almost cancelling in case of A. Hence this option, which was your option B, I think, which will be your correct option. So then we have the next one, which is match the following. So we have three. So this is actually very easy. We have three methods based on the factors, and where the methods are given in this first column, and the factors on which, or the idea on which the method is based, is given on the right hand side column. So what is Patterson method? Patterson method is based on interatomic vectors. So one should go with B. Then what is the sigma 1 relationship and what is the triplet relation? So triplet relation is this one. So if the phases of EHE are same, it implies that this phase will also be the same. So this should go here. And then we have this sigma 1 relation. So you can the details for this relation you can go through the videos, right, of week 10. So we get this as the correct option. Did I covered all the slides? Here, right? Right. So then we have the next question. So if we have n atoms in the unit cell, then how many peaks will appear in the Patterson map? So what is the Patterson map? It is based on the interatomic vector. So here it is given, but let us try to do it on ourselves, right? So if we have n is sorry, it doesn't look like an n. So if we have n equal to 3, means there are 3 atoms. So this can be an atom, this can be an atom, and this can be an atom. So this is 1, this is 2. Okay, so then how many vectors are we getting? It's for the 3 atoms. Okay, so I'll not draw here, then it will make it crowded or complicated. So I'll be writing on the side. So 1, 2, 1 is the self vector. Then we will have self vectors for all the atoms. So we will have 2, 2, 2, and we will have 3, 3. Now the self after the self vectors will come this. So from 1 to 2 we will have a vector, right? If for 1 to 2 we have a vector, then we will have a vector for 2 to 1. Then for 2 to 3 we will have a vector, and then we will have one for 3 to 2. Then for 1 to 3 we will have a vector 3 to 1. So are we leaving anything? I don't think so. 2 to 1 is there, 2 to 3 is there. So how many vectors are we getting? 1, 2, 3, 4, 5, 6, 7, 8, 9 in total. So for 3 we are getting 9, and if we do for 4, so n equal to 4, we will get 16. So it is given by a relation of n square. You have to remember, or even if you don't remember, you can just work it out anytime. So this is what I had prepared for slide here, that for Patterson map, the interatomic vector Patterson map is an interatomic vector map in which each peak corresponds to a vector between 2 atoms in the lattice. So the same thing I had written here. We get n square. So the question which we had was a direct simple question, that if we have n atoms in the unit cell, then how many peaks will appear in the Patterson map? So the answer will be n square. Okay. So this is the last question. What will be the Patterson vector for crystal structures crystallizing in this space group of P21? Okay, so what have we learned? We have learned that Patterson vector is nothing but an interatomic vector. So if we have the space group P21, then what are the equivalent positions? So for an atom at XYZ, for an atom at XYZ, we will have an equivalent atom at position -6, Y plus half, and Z, because of this 2-1 screw, right? So if we just take the differences in between the atomic coordinates, then we will get where we'll get the Patterson vectors, because Patterson vector is nothing but the interatomic vectors. And how can we find out the interatomic vectors? By simply taking the difference in the positions of the atoms, right? So if we subtract this, then for since it is a vector, so vector means the components we have to subtract like x from x and y from y. So we will subtract this -x from x, and we will end up with what is called as 2x, right? Then we will subtract y from subtract plus y, and what we will get, y minus half minus y. This y will cancel, giving rise to minus half. And we will have xy then. So this x is number 1, y is number 2, then number 3 is for the z. So z minus minus z. Z minus minus z. So this is z, okay. So z. This is the thing. And if we look at the options, we will get this. So I've solved all the questions, I think. Yeah. So I've solved all the questions. And what did we learn in today's live session? So in today's live session, so we learned the basic concept of a wave. Then the two methods for solving crystal structure, how to solve the crystal structure. So at first the direct method. So what happens in direct method, it is based on some strong reflections. So a few strong intensity reflections are chosen where their phases will be assigned at random, and then the relationships between the phases are sought for, and the phases are constantly modified until a consistent set is obtained. Then we went to Patterson method, and this Patterson method, in Patterson map, the strongest peaks are always at the origin. So the Patterson map corresponding to vectors between atoms and themselves. So what do we mean by this sentence? In the Patterson map, the strongest peaks are always at the origin, corresponding to vectors between atoms and themselves. So we learnt about the self vectors right here. So we learnt now, so this 1 to 1, 2 to 2, 3 to 3 are the self vectors. So if we plot a Patterson map, so this is the graph. Okay, then the self vectors will simply come somewhere here. So for n equal to 3, we will have what? We will have 3 self vectors, right? So it will just come here like this. For n equal to 3. So in the Patterson map, the strongest peaks are always at the origin, corresponding to vectors between the atoms of the cell vectors, and then the the rest of the vectors come somewhere. So for example, if this is my I'm changing the color to make it so if this is my 1 to 2 vector, then my 2 to 1 vector will come exactly at the opposite. Okay. So actually this Patterson map is always centrosymmetric. You should always remember this. Irrespective of the fact that the crystal structure is centrosymmetric or not, the Patterson map is always centrosymmetric. However, we also have this limitations of the Patterson method, and the limitation is that the structure approach becomes unusable for structures containing like more than 20 to 30 atoms, unless of course there are high atomic number elements. So then direct method and Patterson method, and also the sigma 1 relationship, which is applicable for centrosymmetric structures where the phases can only be 0 or pi or 0. However, for non-centrosymmetric cases there is no center of symmetry and phases can assume any value in between 0 to 2 pi. Okay, so that's all. I think I've covered the assignments till 10. So see you again. Thank you.